Welcome to video 3.4 in our first Principles of Astrophotography series. In this video, we discuss the maximum altitude that a celestial object reaches in the sky. It's called the culmination altitude. And we talk about how this altitude depends on your latitude.
How can knowing about culmination altitudes help my astrophotography?
It can inform your choices about celestial targets. Light coming from low altitude targets, ones that are close to the horizon, passes through more of our turbulent atmosphere, and photos of such objects won't be as sharp as ones that are higher in the sky.
Okay, but why was the airplane sent to his room?
Why was the airplane sent to his room?
Yeah, because of his bad altitude.
Thank you for that. Now I'm getting a bad altitude.
In the next video in the series, we discuss the time of year when objects are well placed in the night sky.
So in this video, we're going to figure out which objects are high enough to see, or even above the horizon. In the next video, we're going to talk about what time of year you need to see those objects. The video is based on section 3.4 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Bode Edwards.
Let's talk sensor sensibility. The altitude A of a celestial object is the angle measured in degrees from the horizon straight up to the object.
So we're talking about the horizon being the horizontal direction, whatever direction you're looking in, that's horizontal. And then the altitude is defined as the angle between the line toward the celestial object and the line toward the horizon. We talked about angle measures in previous videos. They can be measured in degrees, arc minutes, arc seconds, and radians as well. So it's pretty simple. An altitude of 0 is heading is an object that's on the horizon. An altitude of 90 degrees is an object that's straight overhead, called the zenith.
The maximum altitude A reached by a celestial object each day, called the culmination altitude, depends on the object's declination, delta, and the observer's latitude, lambda. According to A equals 90 degrees minus the absolute value of delta minus lambda.
Okay, so you run out of letters really quickly in the alphabet, so we end up using some Greek, and this squirrely looking symbol, it looks kind of like a D, is called delta, and that's one easy way to remember it. Then lambda looks a little bit like an L. I guess it's a stretch to call it an L, but anyway, it's called lambda.
It's an upside down Y.
Yeah, pretty much. I'd say so. Yeah, so the lambda is the latitude, and that's nice to remember because the latitude starts with L and lambda starts with L. And declination, delta, the declination starts with a D and delta starts with a D. So that's happy. So in our book, we actually go through a derivation of the maximum altitude, this A. We use capital letter A to denote the highest place in the sky that an object can reach. And that's given by this formula. Now, these symbols here, this line and this line, those mean that you need to take the absolute value. And what does absolute value mean? Absolute value of 3, so this is the absolute value of 3, equals 3. It's just the number. The absolute value of a negative 3 is equal to 3. So absolute value simply means that if the number is positive when you start off, then you get a positive number out of the deal. If the number is negative when you start out, then you make it positive. That's all absolute value is.
Nice.
Just means make it positive. Okay, and we're going to talk about, I mean, this whole video is basically based on this culmination altitude equation. So, principle 26.
Celestial objects with culmination altitudes less than 30 degrees present challenging targets for astrophotography and may yield disappointing results.
So, comments on that. Have we shot anything below 30 degrees? I think once or twice.
We tried sombrero once.
We tried, no, we
No,
tried
it was-
that Sculptor Galaxy. That's, I don't think we've actually tried sombrero, but that Sculptor Galaxy was way in the lights. It was an ass.
It was yucky.
No bueno. And some people do a pretty good job. And with all of the tools that you have at your disposal, with Blur Exterminator and et cetera, and so that Blur Exterminator is the one that sharpens up images, right?
Yeah.
You can do, but your I mean, you're going to get your best images for objects that are 20 or 30 degrees or above, right?
Right.
And okay, so what we were just talking about is this equation for the culmination altitude. That's the maximum altitude. And what we're showing here is 3 objects with different declinations. So the declination of Bode's galaxy is 69 degrees. The declination of the Orion Nebula is -5 degrees. And the declination of the Tarantula Nebula is -69 degrees. So let's do a little bit of math here. Let's find the maximum altitude of Bode's galaxy. And I should say about this figure is that I'm assuming that Bode's, Orion, and Tarantula are at the same right ascension, that they all have the same right ascension. So they're in the same part of the sky as you move throughout the night. They aren't, but for the purpose of this illustration, it just makes sense.
Yeah.
All right, so let's apply this formula to Bode's galaxy and see what happens. The culmination altitude is going to be 90 degrees minus the absolute value of the declination of the object, which is 69 degrees, minus the latitude of the observer, because your point where you're looking from on the Earth actually matters here, matters a lot. So for this observer, we have, we're assuming a latitude of an observer of about 33 degrees, which is lower than our latitude, so it'd be down in Florida, I'm not sure, somewhere in the United States. And so for this latitude of 33 degrees, then we do the math. So the first thing to do is to do this subtraction. We'll have 90 degrees minus 69 minus 33, which would be 36 degrees. Then the next step is to take the absolute value of 36 degrees. Well, 36 degrees is a positive number. And the absolute value of 36 degrees is?
You don't have to get any more positive than that.
It's as positive as it can get. Minus 36. So absolute value of 36 degrees is 36 degrees. And 90 minus 36, I think, should be 54 degrees. So what does that say? It says that Bode's galaxy is at an altitude above the horizon of 54 degrees when it reaches its maximum altitude. That's as high, the highest that it can get in the sky. And what is that angle? Well, remember that angle, the altitude angle, is the angle from the horizon, so that's this line right here, up to the galaxy. And that angle is, according to our calculation, 54 degrees. Hallelujah. So a culmination altitude of 90 degrees would have been straight overhead toward the zenith. A culmination altitude of 0 would have been straight toward the north horizon, right? but we're talking about 54 degrees, which is a little more than halfway between the horizon and the, yeah. So Bode's galaxy, great from a latitude of 33 degrees. It gets up to 54 degrees, that's awesome. What about the Orion Nebula? Let's do that one. 90 degrees minus, so we need the declination here of the object, which is -5 degrees, minus your latitude, which is 33 degrees. Okay, so a -5 minus a -33, both numbers are negative, and so what we're going to do is add them and then take the negative of that. So now the culmination altitude is 90 degrees minus the absolute value of the negative of 5 plus 33 is 38. Now, the absolute value of a -38 would be,
Just make it positive.
make it positive. And the difference between 90 degrees and 38 degrees is 52 degrees. 3 plus 5 is 8, 8 plus 2 is 10, perfect. So this culmination altitude of the Orion Nebula is pretty darn close to the culmination altitude that we got for Bode's galaxy. But in the case of the Orion Nebula, it's going to be in the southern sky. So this part of the sky right up here is the northern sky. This part of the sky right here is the southern sky, and we'll talk more about that later. And so we're going to be measuring that culmination altitude from the southern horizon up to the object. So in this case, the culmination altitude is going to be 52 degrees measured up from the southern horizon. Good so far?
Good.
All right, one more. The Tarantula Nebula. I'm sorry. I blew that. Let me do it down here. A is 90 degrees minus, I want the declination of the object. It's a -69 minus the latitude that we're looking from, which is 33 degrees. And you can substitute your own latitude wherever you are on the Earth. And all this works just fine. All right, so let's do the math. We got a -69 minus 33. It's going to be -102. That's right, 69 plus 33, that'll give you 90, plus 9 plus 3 is 12, 102. And the absolute value of a -102
102.
is 102. Now, finally, the culmination altitude is going to be 90 minus 102. And 90 minus 102 is a -12.
Yuck.
That's for the Tarantula Nebula. What does that tell you? It tells you something very important about the Tarantula Nebula as viewed from a latitude of 33 degrees. The embarrassing thing is that you will never see it in your sky. You're out of luck at 33 degrees. You're going to have to go down to Australia or South America or Antarctica to see that, to get your latitude now low enough so that you can see the Tarantula Nebula. So this formula is very powerful because you can, it tells you whether you can ever see the object in your sky. What this basically is telling you is that during the course of a day, the highest ever that this object is going to rise in your sky is -12. And so any comments about that?
No comments.
Okay, no comment.
It's just a bummer for all of us in the Northern
It's
Hemisphere.
a bummer, yeah. So we have a collaborator down in Australia, Caroline Peake, who has taken took us a beautiful image of the Tarantula Nebula
Yeah.
It was beautiful. And then we processed it and worked with her on it. But it's, meridian.
Principle 27, meridian. An observer's meridian is the circle that includes the observer's northern horizon, zenith, southern horizon, and nadir. Or
Okay.
nadir.
Yeah. Now, if you want to do mater
Like nadir.
in cars, yeah. All right. So what is this? The meridian is this dotted red dashed line that goes from the northern horizon. That's when this guy looks this way, he's looking toward his northern horizon. He's looking toward the North Pole. Toward his zenith, which is straight overhead, and then looking to his southern horizon. So it's this circle, but it also includes the nadir. So I was talking with my wife about this, and she was saying, well, it's not really a circle. It's a plane. And she's not wrong. It's a plane that's defined by these points. Where you are, you look straight overhead, you look straight north, you look straight south, look straight down. That creates a plane, and that's called the meridian. Okay. So culminations.
Principle 28, culminations. Upper culmination is the daily east to west meridian crossing of a celestial object when it reaches its culmination altitude A. Lower culmination is the daily west to east meridian crossing of an object when it reaches its minimum altitude.
Okay, so what does all this mean? The figure that we've been looking at so far has been the situation at upper culmination, when the object reaches its maximum altitude. So that's why this is labeled this way. And as you can see, we've got North and South America in the field of view. Now, what happens after 12 hours has passed from this point where these objects are reaching their upper culmination? And the answer is the Earth has rotated halfway around. So now as we're looking down at the Earth's space, we're seeing Africa and Asia and Europe and Australia instead of North and South America because the Earth is rotated. Now, at the same time, we're interested in these three same objects, Bode's galaxy, the Orion Nebula, and the Tarantula Nebula. And what are the directions to these objects? Well, if you compare this direction to Bode's galaxy, it's up and to the right, as seen from this perspective. And then after the Earth is rotated for 12 hours halfway around, you're also seeing the direction to Bode's galaxy being up and to the right. So explain that to me, Ren. Why are those two directions the same, or at least very close to approximately the same? When you're looking at Bode's galaxy, you're always looking at this in the same direction, regardless of the time of day, as viewed by an observer that's outside.
Because it's circumpolar in the north.
Yeah, it's circumpolar. And also, Bode's galaxy is not close to the Earth. It's really far away. And so, if Bode's galaxy were right here, up close to the North Pole, then when we looked at it over from this side, we'd be looking that way. And when we looked over from this side, we'd be looking that way. But it's extremely far away from the Earth. And so, the Earth's diameter pales in comparison to the distance to Bode's galaxy, and as you get further and further away, these lines to the object get closer and closer to parallel.
Are you saying we're insignificant?
No, I'm saying that, I don't know what I'm saying. The Earth is really small. That's what I'm saying.
Great.
It's a small world
making me feel
after all.
small. Yeah.
Small world after all. So that direction that you're seeing toward Bode's galaxy is the same. Same thing with the Orion Nebula. It was down and to the right in this diagram. Well, it's down and to the right in this diagram also. And this is one of the questions that Ren had early on when he was trying to understand these diagrams. Is he's saying, well, why don't we, why aren't those directions different? And the reason is that these objects are so far away compared with the size of the Earth that the lines are effectively parallel. Okay, but what does this mean? At lower culmination now, Bode's galaxy, its altitude is from the north horizon up to the line of sight to Bode's galaxy. That looks like a pretty small altitude. It's just skimming the horizon.
Yep.
And then Orion Nebula is in a very embarrassing position.
Very.
Because we can't see it at all at lower culmination. Tarantula Nebula, we can never see it at all. But the Orion Nebula is visible at upper culmination, but hidden behind the Earth at lower culmination. So to illustrate the meridian, I'd like to go back to an annotated long exposure photograph that we looked at in the last video. And this is a view, this is in Arizona. In the United States, in the northern hemisphere. In fact, it's at Kitt Peak National Observatory in Arizona. And this is a view of the northern sky taken from the northern hemisphere. So if you're in the northern hemisphere, you can see the North Celestial Pole, where Polaris is, and you can see the stars. So east is to the right of north. If you're looking north and you look along your right hand, you're looking east. West is to the left. Stars rise in the east, set in the west. So therefore, these circumpolar stars are going to be circulating counterclockwise. Let's take this circumpolar star right here. It takes 24 hours to go around the circle. Where it reaches its highest point, namely where it crosses the meridian, this vertical line, this red line, goes from the northern horizon through the North Pole, North Celestial Pole, directly overhead, and then to the southern horizon. So the meridian is always going to be perpendicular to your horizon. So this is the horizon. And then this here is the meridian. All right, well, this particular star that's circulating counterclockwise crosses the meridian right here. That's called upper culmination. And the upper culmination is where it reaches its greatest altitude, which we call the culmination altitude A. Then 12 hours later, half a day later, it's traveled around here. Now it's passing through the meridian again. This is called the lower culmination. Okay, so that's what happens with circumpolar stars. They reach upper culmination and lower culmination once each day, separated by 12 hours. Both of those culminations are above the horizon. What about seasonal stars? What about this a star that's right here? Well, he's going to reach, well, it's out of the picture, but let's look at this star right here. He reaches upper culmination above the horizon, but when he's traveled all the way down to here, he's going to reach lower culmination below the horizon. So the only culmination that you can see, the only culmination for which the star is above the horizon, is the upper culmination for seasonal stars. And of course, for antipolar stars, neither of the culminations are above the horizon. Both culminations are below the horizon. That's why you don't see any antipolar stars in this figure. Now you can reverse and say, okay, well, this figure is for a northern observer looking toward the northern sky. Well, what if you go down into the southern hemisphere and you're in Australia and you're looking toward the southern celestial pole, the only difference there is that instead of north, this would be south. Instead of east, this would be west. Instead of west, this would be east. And instead of the stars circulating counterclockwise, they're going to circulate clockwise, like we talked about before in the previous video. So these guys are going to rise in the east, travel around in a clockwise direction. All right, this is a figure that we also looked at in the last video. This is in Iran, which is in northern hemisphere. And we're looking toward the southern, we're looking at the southern sky. And so instead of east here will be west, this would be east here. And stars are going to rise in the east, set in the west. They're going to travel from left to right across the sky. And what kind of culminations do we see? Well, this particular star crosses the meridian right here. Is that an upper culmination or a lower culmination? It's an upper culmination. And its altitude, its culmination altitude, which we denote by A, is whatever it is. It's the angle above the horizon for the upper culmination. The lower culmination for that particular seasonal star is going to be below the horizon. You'll never see it. And then you can also reverse this, of course, for a southern observer in Australia, for example, in the southern hemisphere, and you can look toward the northern horizon, then this will be east, and this will be west, and the stars are going to rise in the east and set in the west. Again, the upper culmination will be whatever it is, the angle from the horizon, and again, antipolar stars are simply not seen.
All right, principle 29, culmination visibility. Circumpolar objects reach both culminations above the horizon. Seasonal objects reach upper culmination above the horizon and lower culmination below the horizon. Antipolar objects reach both culminations below the horizon.
So we talked about these three types of objects: circumpolar, seasonal, and antipolar in a previous video. I think it was the one we just shot before this one. And luckily we have an example of each of these three types of objects in this diagram. Bode's galaxy is circumpolar for an observer at a latitude of 33 degrees. So this bad boy is circumpolar. You can see it at lower culmination, and you can see it at upper culmination. You can see it both all the time. It's always visible. The Orion Nebula, on the other hand, is a seasonal object. So it's in this orange region here. You can see it at upper culmination, but tough luck at lower culmination. And then finally, Tarantula, so this is a seasonal.
Our giant bulgy Earth is in the way.
Yeah, darn Earth.
I mean, our small world.
Very small world, yeah. And this is an antipolar object that is invisible both at upper culmination and at lower culmination. Okay, we did that.
All right, principle 30, daily culminations. Stars and deep sky objects reach the same culmination altitudes every day, each day of the year, at a time of day or night that depends on the right ascension of the object.
Okay, so this is a really important point. And as we got thinking about, as I started we're working on our observing list, and we're trying to understand what objects we can see and when we can see them. At some point, I just realized, and then Ren and I talked about it, that they reach upper culmination every single day. Well, why is that? Well, because here's upper culmination for Bode's galaxy, for example, and we reach lower culmination 12 hours later, and then another 12 hours later, it's back to upper culmination.
Yep.
It's hitting that maximum peak every single day. The key here, though, is that it might not be reaching upper culmination at night,
Right.
when we can look at it through our telescope. I mean, it doesn't do you much good. The Bode's galaxy is reaching its upper culmination in the middle of the day. You're not going to be able to be shooting it at that time. But they reach their upper and lower culminations every single day of the year.
They should make a sun filter so we can filter out the sun and shoot it during the day.
There you go. They have to filter out our atmosphere too, because our sun eliminates our atmosphere. Yeah. Work on that. Maybe one of our viewers can figure that one out. Okay, culmination placement.
Principle 31. For an observer at latitude lambda, a celestial object of declination delta culminates at the observer's zenith if delta equals lambda, culminates at the observer's northern sky if delta is greater than lambda, and culminates in the observer's southern sky if delta is less than lambda.
That's right. Okay, so here's the geometry. There's the latitude, lambda of, in this case, 33 degrees. Latitude of 0 means equator. Latitude of 90 means North Pole. Latitude of negative 90 means South Pole. And then this is for an object that culminates in the northern sky. So, for example, Bode's galaxy example. So this, I don't know how much I want to say about this, but the delta minus lambda is going to be a positive number. And when we take the absolute value of delta minus lambda, then we're going to get a positive number. And then we're going to subtract that from the latitude, and that'll give the, or subtract that from 90 degrees, according to, this guy here. So we've got delta, subtract lambda, take the absolute value, which is going to be positive for an object in the northern sky, and then subtract that from 90 degrees in order to get the altitude. And then in the southern sky, the object's declination is less than the latitude. So here's the latitude, and here's the object's declination. And so when you take delta minus lambda, that's going to be, lambda is bigger than delta, so you're subtracting a bigger number, and you're going to get a negative number, which is embarrassing.
Right.
If lambda, the latitude, is greater than the declination, lambda is greater than delta, then the object is going to culminate in the southern sky. And if delta is greater than lambda, then it's going to culminate in the northern sky. If delta, the declination of the object, equals your latitude. So here's the latitude. Delta is measured from the same direction, the declination. If that delta equals lambda, then the object is going to be right at your zenith. That's where you get, that's ideal. I mean, if it's going to culminate at the zenith, you're going to get the most time on that object. It's awesome.
Principle 32, culmination dependence. The closer the declination of a celestial object is to the observer's latitude, the greater the culmination altitude, and the higher the object will rise in the observer's sky. Objects whose declinations differ from the observer's latitude by more than 90 degrees remain always below their horizon.
So that last little bit right here pertains to observations of the Tarantula Nebula by somebody at a latitude of 33 degrees. Remember, we took delta minus lambda, took the absolute value, subtracted that from 90, and we got a negative number of negative 12, I think it was.
So if it's a negative number, it's antipolar.
Yep.
Yeah.
Yep, that's exactly right. And so that's the example of the Tarantula Nebula. All right, and so the closer, and so this graph sort of captures what we're talking about here. Delta minus lambda is a declination minus the latitude. If they're equal to each other, then delta minus lambda is going to be 0.
Right.
And we're going to be right here. And that object is going to culminate, the culmination altitude is going to be 90 degrees, and it's going to culminate at the zenith. If delta is greater than lambda, so this region here, then the closer you are to them being equal, the higher you're going to be in the sky. And the farther apart that they are, the lower it's going to be in the sky. And then if they differ by more than 90 degrees, it's going to be below the horizon. So then the same thing over here. The closer you are to delta and lambda being equal to each other, the higher it'll rise in the sky.
But really, this area below 30 is useless.
Yeah, 20, 30, 25 degrees, I mean, somewhere between here, you can photograph it. And that image...
Well, you're not going to get long on target, and you're going to get really noisy data.
That's exactly right. You're not going to have very long on target because it's going to rise and then spend an hour or two above the horizon, or not very much time above 10 degrees is just awful. But that image that Pat Neely took of the Trifid, I think its culmination altitude is something like, at our latitude, I think it's around 24 degrees. He did all right.
Wow.
He did okay. So astrophotographers are a innovative group. They can figure it out. Thanks for watching.
And we'll see you next time.